and the microphone is here.
Okay, and again, please interrupt. This is not a real class as well, so interrupt me if you have any questions. If you see I'm talking about something you already placed there, interrupt me. I mean, let's make it as interactive as possible because we already had a recitation yesterday, so I don't want to do another recitation at all. So, okay, I call this how to make a computer, okay, which is basically, okay, let's imagine that we have to start from the ground. Now let's imagine that we have to design everything you will use on Fab Academy regarding electronics from the ground. So how we'll do it, okay? And why I use the word computers a lot? Well, basically, because all the work that you will do in Fab Academy on electronics, it's based on what's called digital electronics. That we'll learn it in a moment. But as you will see in Fab Academy, we don't do analog electronics. We don't learn how to build like full analog synthesizers. We might maybe use some amplification, what's called an operational amplifier sometimes. Like we'll learn some small tricks that you need to know about analog when you are reading a sensor that sends the volts so it perceives the things in an analog way, not in a discrete way, in a continuous way. But when we go into Fab Academy in general, everything is about digital electronics, and so this is focused on digital electronics, and that's why I'm going to try to explain what digital electronics are a little bit. So, well, first of all, important to know, just a few things to start, okay? Computing is not just about computers. I mean, let's forget that when we talk about computers, we talk about Macs. There's many things that can be a computer, and there's many ways to compute. So important, as I say, computers are much more than laptops and servers. There's computers around you all the time, and we think it's increasing exponentially. Like, if you think your house on the 90s, you might have maybe a few computers aside from your Windows 95 computer. Maybe you had one in your video, if you had a way to program it, and maybe you had one inside your AC. You had an AC with a remote. And you had quite a cool TV with a nice remote where you can switch channels. It had one, but just these ones. Nowadays you have them everywhere. If your fridge has a small, not even a screen, even a few LEDs that show you, sure there's a microcontroller there. And of course, if you think in the cars nowadays, there's hundreds of them. So computers are everywhere. And not just computers, so connected computers, as we know. No? Like we were at this point that the only thing we had connected was our computer, and when we turned the modem on, right? Now we have things connected around you that you don't even realize they're connected. No? I mean, this phone here is connected to the internet directly, and your phone is connected, and many gadgets that you might have in a way or another connect. You have one of those things for tracking your activity or when you do sport. If you have, even watches can be connected. Even if they're not straight, they go through your phone and connect to the internet. So we have a bunch of computers connected around us. And it's important to understand that computers can be everything. You can think of computers of things that don't have on the screen at all, like the computer that takes care of your airbag in your car, or the computer that takes care of managing the engine in your car or in your fridge, and on an elevator. And just think how many actions you do, which in a way or another are connected to a computer. And the computers that you don't see, the utilities, the computers that control the gas and the water and the electricity that arrive to your house. So there's computers everywhere. So important to understand also, and just we'll go on this in a moment. Computers are not silicon or binary. Okay, so this idea that computers use ones and zeros, or this idea that computers are made of silicon, is not that that's the let's say that's not the gems, and that's not the philosophical stone that you need to compute. We use them because they are convenient, because using silicon turns to be an accessible material to make semiconductors that's available, and that's why we went for silicon. There's others. And binary, basically we do it because it's reliable, because it creates less problems than if you design a computer that's needs, instead of managing two states, yes or no, it needs to manage a states from 0 to 10, for example, and make it decimal. So, and as I say, computers, they don't even need to be digital. We make them digital because it's much more convenient, and it's what allows us to have the revolution that we are seeing. But in fact, the first computers were fully analog. So think on a clock, like the clock that you might have in your grandparents' house that's ticking continuously with a pendulum. That's somehow we can think of it as a computer. It counts time, it manages information, it counts time, minutes, hours, it even might have a calendar, and everything it's completely analog. These are just wheels which is moving, and on a continuous manner they keep counting time. And in fact, at the beginning of the 21st century, that's how computers mostly operated. So the first computers that, as everything around us, started by the military. So the first computers that they designed to calculate trajectories of ballistic trajectories, of bombs and missiles, that were analog. And that's, imagine you want to calculate how much is the inclination and how much you need to load the projectile to go to a certain distance. This is basically a bunch of parameters, that you can put together as an equation, This needs to be 2 times this, needs to be half this, so I arrive there. You can map this into gears of different sizes, You can even map it to voltages of less or more voltage, and these are continuous, You don't divide them on steps. It's continuous. We'll learn about this later on a little bit, but so, in general, my opinion, why it's important to learning the core principles, because it helps us to be creative. So if we learn the core principles about how things work, instead of always looking for off-the-shelf solutions, instead of us living inside a black box, we'll be more creative, because when we have a problem, we would be able to think that there's other ways to solve it. We might not know the way, but it might open our mind and think, okay, there's different ways I can solve that. And I think that creativity is what we need to solve the problems in a Pavlov way, Because if no, we'll be solving problems as the industry does. And the point of Pavlov is to solve problems sometimes in ways which the industry never thought about them. And that's why sometimes, without pretending to be a scientist or a computer scientist in 3 months or 4, it's good to go and say, okay, well, these concepts are interesting. Let's say no one is able to understand them at first. I don't even understand many of them, but they help you. Okay, so just a few things before we move forward. So if we agree that we need to understand a bit these 2 principles, okay, before we move into understanding a little better what a computer is and the kind of computers we use at Pop Academy. We can have computers which are analog or digital, as we said, okay? We'll go about this in a moment, okay? But basically, think of analog as how you experience reality. You experience reality as a continuum. What that means, when you look at this table, you put your hands and you measure it, and you don't need to say it's like this or it's like that or it's like that. No, you feel it, right? You feel it, you move your hands, there's a point, not a table, that's it. When you count, well, counting maybe not a good example, but how do you feel time? You feel time not with seconds, like 1, 2, you feel time as a continuum, right? Your brain doesn't feel like, oh, okay, this happened in second 1, this happened in second 2. No, you feel as a continuum. You don't have this sense that the reality is divided by chunks, like 1 second, 2 seconds, 3 seconds. Even so basically, when you don't divide things in chunks, let's say, when you don't have to define things on a scale, when you see things as a continuum, when you don't have to say that's 24 millimeters or 25 millimeters, when you can say, well, that's between 24 and 25, and you don't need it there, And you don't have to divide 24 and 25 and make it a little smaller to another. No, you perfectly can say that that's between 24 and 25, and your brain understands that perfectly. So that's because we are digital computers to make that, and to think much more. But why we use digital? We'll look at it in a moment, but we use digital because it's easier, and it makes things much more powerful. But we'll go in a moment into that, okay? Electronical versus electromechanical. We said in a moment, you can build a computer with gears, right? You can build a computer even using relays, but that's how computers were built, as I've said, up to half the 21st century. But electronical means they're far more robust. And as you know, the revolution here is being what's called transistors, and everything that you'll see inside these computers that we'll use these days, these microcontrollers, new computers, everything that works on the same principle. There's not, let's say, there's haven't been a new concept that surpasses the idea of the transistor. We've just been getting this already, how to make it smaller, better, cheaper, and more power efficient. Binary versus decimal. Well, we'll look this in a moment later on. It has a lot to do with the ideals of analog and digital, but basically think that you can count in any system. We count in the system of 10, we can count in the system of 2, we can count in the system of 12, 16, or 6. We use binary because it's far easier to have a system where you count things by having voltage or no voltage, it's like water or no water, than having a system where you can have 10 different levels of water, okay? Because imagine that suddenly a pipe has a leak and it increases a little bit. Okay, you might be confusing a 9 for a 10 easily, or an 8 for a 7. Instead, if we have something which is water or no water, it's much more easy that we can build things which are really low. And reliability is important because if we won't be able to design things which are really, really low, we won't be able to make them that small. And by making things simple and really low, it's why they can put thousands of transistors inside something and make it super small and making that cost $1 or less, no, €1 or less. And really important, general versus special purpose computers. So basically, the computers that we have around, we can call that they are general purpose because we can put any software inside and they are designed to do many different things, right? You can run Photoshop, you can code VR Reader, you can run Chrome, you can even change OS, put Windows, put Linux, put Mac, okay? Special purpose computer is like a computer which is designed to do one thing. And we all had them, at least a few years ago. We had calculators in school to do math, you know? And that's a special purpose computer. There's a software inside that is just designed for a single purpose. And so that once the components inside are tied together to do a single thing. Instead, nowadays, most of the things we see around, they are general purpose. Even if they are just inside the microwave, we could easily program the chip to do something else, maybe, because it's easier just to have computers which can do everything, and then we just code inside and make them do what we want. So the industry doesn't need to produce a specific computer for everything. We can just have it general computers in different kinds of prices and choose the one we want and put the code inside. So it won't be like this the whole session, and just to get a little bit on the thing. So the computers that we'll be using in Fab Academy, the computers that we have in our desk now, the computers that we have in our pocket, based on this definition, we could say that they are digital, okay? Because basically they have a discrete way of thinking on information. They are electronical, there's no moving parts inside, there's no mechanical parts inside at all. They are binary because they count with zeros and ones. So they can kind of do any number you imagine, but with zeros and ones. They are general purpose in the sense that we put code inside and the code does what we want them to do, right? It's not that we have a microcontroller which is just for driving motors and a computer which is just for Photoshop. No, general purpose, okay? And computers. So, what I'm trying to say by this is that basically this approach has been followed by the industry for the past years. And basically a standardization, which is what happened here at the end, allows us to make things cheaper, faster, and it allows us to build upon others' work. And that change has been massive. Um, if you look inside any electronic gadget around that you have, you will see they all look the same. And I recommend you to this. It's a way I think you can learn a lot. When you start to do electronics, just open electronics that you have around, or look for features on iFixit and these kind of web pages of things that you own, and you will see how they look inside, and you will see there's been a massive change. So, for example, let's imagine a video recorder, right? A video recorder, or even let's say, yeah, I think a video recorder might be an example, which is good. A video recorder as the ones we had when we were kids. That thing inside, it's full of custom parts, which are designed for processing analog video signals, put it inside the recorder, record on the tape, get the image out, and throw it out. And all this is full of different components that are specific from the video industry. If you look at the DVD now, a DVD inside, it's as any other electronics that we have. There's a power supply, the video had it too. There's some device that reads the laser that's feeding, and we have a computer there that just gets what comes from the DVD, does some processing with the image, and throws video in digital to the HDMI port. And that is more computer. In terms of price, it's different, but in terms of the core architecture and how it's coded, it's the same as your laptop, it's the same as your phone. If you go and you open any sort of like IoT gadget, like for example, this kind of Nike Fitbits, I don't know, this kind of sport bands that you can wear, you go inside the same, like an accelerometer, that's the input, it's not a laser from the DVD, no. An accelerometer, some microcontroller that gets the readings from there, maybe a Bluetooth module, so the thing reads the accelerometer and talks to the Bluetooth module and send it to the phone when it's connected, But at the end, the architecture of all of them is the same. And in fact, even most of them are coded using C++, which is the same language that macOS, Linux, and Windows are written to. So this standardization basically is what's helping us to be able to make things so cheap. And that's why before, usually like consumer electronics were more expensive. No, we've been seeing how they drop in price and price and price. But that's also why when we open something now, it's always, you don't see anymore like dedicated parts of hardware. You know, it's like you don't see anymore. Oh, that's something that I can use for that or the other. It's just something there which is always the same, which is a processor that's connected to some peripherals, receives some information, process something, and outputs it. So basically, I think we need to understand that's the power of digital, right? That's the power of basically the information or the DVD or the Blu-ray is stored in ones and zeros. So the processor just needs to get these ones and zeros, process these ones and zeros, and send this information through the HDMI port, which is fully digital. So we just need to manipulate ones and zeros. We can think on ones and zeros, we can think on numbers, but at the end, we just doing like operations in numbers up, down. So, okay, that was a bit introduction, so we get a few ideas. Going quickly, okay? Electronics, first of all, digital versus analog. Well, it's always, I would say it's this kind of thing, it's easy one to get it, but sometimes it takes a while, no? But one thing which is easy to understand, no? As I said before. So, imagine us measuring the table, okay? Our hands are continuous. Imagine me talking. The frequencies I generate with my voice, they are not 40, let's say 440 hertz and then 442 hertz. They can be anything between them, you know. Our body doesn't work on a matter of fixed scales of that most of the time. So that can be my voice talking, okay, or that can be my hands moving, okay. So that continues. We found a way which is okay. Let's basically get something which is continuous and let's chunk it into a small parts and measure each part how big it is. So what we basically do is that we have something like this, okay? We have something that can be, let's say, a wave, okay? It's my voice. And we apply a grid on top, you know? We apply a grid on top. You know when you use this paper that you used to use it for to make charts, so like millimetric paper, you know? It's like you apply a grid, like a notebook grid on top. Okay, and then suddenly, when you get something like this, you know? So you say, look, have my grid, and I'll say every time that on my grid I have an intersection between the horizontal, the vertical, let's say, columns, and it intersects with my wave, I would just look to the point which is closer. So see, if you look here, it's not getting the point there because it's not on the grid. So just I will put a point on the grid, and you end up with something like this. Okay. Well, what's good about this? What's good about it is that I can quantify it now. So quantifying means that now I can count how many of those bricks I have here. No, I can say, look, 1, 2, 3, 4, 5, 4, and I can count these. So I cannot say at time 1 or time 0, we want to go using 0, let's say. At time 0 it's 0, at time 1 it's 4, at time 2 it's 5. And in this way, something that was not possible to represent using a numerical value, now I can represent it using a numerical value on a really easy way. And that's basically when you talk to your phone, that's what your phone is doing. When you listen to audio, when you watch video, that's how it's going on. I think with audio it's really clear. So imagine yourself talking through the phone, okay. Instead of having to send a complex wave over the lines, a complex wave is always a problem because imagine that I have this thing, which is sent over here, and imagine that suddenly I just start having some noise on the line, okay? So imagine like I just start having some noise around. This thing would vary. Instead, if basically I just had a digital representation of that, which is would be a set of numbers one after the other, right? It's far easy that this information keeps intact and I'm not losing it. That's quite a big topic. It's called error correction, and you can read a lot about them, so we won't go on that. But basically, on the electronics you'll be doing, you'll see that you read sensors, which are analog, like a temperature sensor, like a potentiometer, and basically you'll be doing this procedure. But aside from that, it's interesting to understand that the way all the computers we have work is this way. So our computer doesn't store magnitudes in a continuous way. It always applies grid on top of them, right? And through that grid, it finds what number it needs to be. And then you'll say, oh, how you store commas in a computer, right? Decimal points, no? Well, there's something which is called floating point representation, which is what's used here. But I think we can avoid it. So basically, I think the beauty of that, from a conceptual point of view, it's the idea that, so that's basically the Phone Express. That was the service that was used to send basically letters from the east to the west coast of the United States, and that's people putting the lines for the telegraph, okay? So suddenly, instead of having to design a medium for each specific set of information, you have all the information represented on the same way. So instead of having to have a system to send letters and one to send video and one to send voice, if you turn them into ones and zeros, then suddenly the medium doesn't care about this. So you can send any information that you want, right? So that's why we have telephone lines that were designed to carry voice, and now we are sending videos over it. And the internet was designed for text and email and the web, and now we are doing Skype conversations on top of it. And that's the power of it. And that's the same. That's why all microcontrollers that they were not designed to do things that we'll be able to do with them because they accept these rules, which is we'll turn information into ones and zeros. So I don't need a microcontroller which is for driving the LEDs, one which is for reading temperature. I can turn everything into a representation that's easy to process and that's discrete in the sense that it has a fitting number of elements. So, moving forward. Okay, hardware. So that's a PCB. That's a PCB that you'll be building, right? Yeah, yesterday on your slab, no? It's exactly still this one, yeah.
Oh, wow.
Well, there's few changes
This
maybe.
and now
Okay.
something like 6 more.
That's big. That's a cool thing. So, a few concepts that help when we look at electronics. So, uh, you look at this board, okay, and you would say, well, first of all, I mean, what is this about? It's like I put something here with a lot of pins, and then I have to start putting things around. It's like, well, why I cannot use that and just have a small components around? Or why, instead of having a big piece of that, I have all these components around? Why we cannot have one piece like this that's the whole thing, no? And that's it. I solder it on top, and I put the USB, and it's fine. So, well, at the end, the answer here most of the time, as everything that has to do with the industry, it's not technical. It's more about convenience, it's more about economy. So these are just design blocks. It's like Lego bricks, you know. So we have this block here. That's a microcontroller. We'll learn later on more what they do. But that's basically it's a small computer. So Atmel, which is the company that makes them, thinks, okay, we'll do a microcontroller which should be cheaper than €2, and it should be able to run around 8 megahertz. So it's enough for applications that might demand quite fast computing, like maybe something has to do with audio or something that has to do with reading a gyroscope on a car, so you know, or an accelerometer, so you know when it's crashing. It needs to be in a small package, okay. And then they design that and say, okay, that's what we think it's good. We'll make tens of thousands, millions, so the price is really cheap. But then, okay, you need to adapt these to the needs that you want. And they say, look, instead of making one for each specific need, we'll make one which basically it's more generic, and then people will put the components around to make it suit for the needs it has. So in this case, for example, we have the microcontroller, and we need some connectors for programming. Well, they could put the connectors on top of that, but they say no, because some people like this connector, some people like other connectors, etc. And they put it, and we put the connector here. Oh well, you need a clock. You need a clock to time the controller so it knows the exact time. And when it does, the USB is not losing time. No, time is really critical on computers. Imagine that things won't be in time. You won't be able. Then you will start listening audio to your computer and it will slow down. And you will be watching videos and you won't see them at 20 frames per second. And things will start going slow. So you need time. Time is important. And all the communication protocols they depend on time. So you put a clock here. And why you don't put it inside? Well, because it's like, no, let the guys customize and make it as they want. No? So maybe someone wants a car which is faster, slower, cheaper. Well, you would also need a few other things, as for example, if I'm right, you need also two diodes here to prevent the flow, and these are two pull-ups here. So basically, you need a bunch of components around, okay, which at the end, they are not inside the chip, just so you can customize and make with the chip more things, okay? If they will put them inside, the chip will be a little more expensive, but more at least you will be able to fit it to less applications. But then let's think for a moment. Okay, what's the chip inside? What's that thing here inside it is? It's like, is that different than these things here? And the answer is no. So basically, what you see inside any of these microcontrollers, inside the processor, it's just a bunch of transistors, of capacitors, of resistors put together on a single package. So, and I think I have here an image that might help us. So computers at the beginning, like when they started to become a little, not big but known in the 60s, let's say, they were built using what's called discrete parts. So you'll have a PCB, right, like the one you'll build, and then we'll put here the transistors and the capacitors and everything, and then we'll build a whole computer with that. So you won't see inside a computer anything black like this. You won't see that. You will just see the components, the discrete components, separate one from the other, right? Because they didn't have invented that technique, okay? And it was for them that it was cheaper to make it that way, okay? And then in fact was something cool to know, like one of the first times that this idea of making things out of silicon on a single, a small, so basically joining a bunch of capacitors and resistors that do a specific function and putting them into a black box and making it a small, that was mostly done by the first time, or at least put in production for the Apollo computer. So they needed that computer that when the rocket was orbiting the moon, they will have that module that will go down to the moon and will land on the moon and then back, connect with the rocket, let's say deorbit from the moon and orbit on Earth and arrive to Earth. So they needed, for the first time, like a really small computer. And they decided to go for integrated circuits because they were smaller. Because imagine building a computer with cars like this is what made the computers be really big, right? And less efficient in terms of power because all the components are separate ones from the others, you need to cover longer distances, etc. So one of the first times that they did this was for the Apollo control module computer. And basically, and to detail a little bit more if you're interested, how this happens is, so we understand that if we want to make a computer, we'll need basically, and we'll go into detail later, but we'll need to put together a bunch and thousands of transistors mostly that would help us to do the logic, will help us to count, will help us to store information, will help us to multiply. So before you would put all these things one on top of the others, you'll buy the components as on this image here, right? And we'll make cards with them so you can swap them. And so what they decided this process, it's no. As we make with silicon, we make transistors. So they found a way that they couldn't just make transistors with silicon. They found a way that they could also make resistors and capacitors with silicon. And then they said, look, most of the electronics components that we need, which is resistors, capacitors, and other transistors, we can make them out of silicon. And they say, okay, so instead of having to cut silicon and make, okay, that's a capacitor, that's a resistor, that's a transistor, why we don't do it on top of a sheet of silicon, and we just change the properties of silicon, and so from a piece of silicon, we'll obtain something that's something like this whole thing, but miniaturized, okay? So they found that process, and that's how the electronics industry went crazy, because they found a way that you don't need to move with your hands things. So how this happened is from a big piece of silicon, through a light process, they modified the silicon to get these different properties and become a transistor, a capacitor, a resistor, etc. And basically, that things, of course, are designed with computers, so it's not that someone is drawing them now. Well, in the beginning it was like this, but now basically imagine that you say, okay, I need a row of 1,500,000 transistors for my memory, okay? And you just code, okay, one row, 1,000 transistors, and it draws that, okay? And then when you have all this row, you simulate everything in software, okay? You run touch components with your hands, and then finally what they do is that through an imaging process, which you can think about it as similar to any print process, you know, when we print books or when at the end, we can say it's not that different than how a laser printer works, a traditional laser printer. It's different, but I think the idea of using light, right, as on the laser, and using a mask, which is this. So they basically change the silicon properties, and then they just put some metal legs around so we can actually touch it with our hands and solder it on a board. It's important to understand here that when we talk about this, we talk about an integrated circuit. No. So every time you see one of these black boxes, don't think every time you, it would be good to open electronics once you look at them. No, when you start opening electronics, I recommend you to do so. At least, if you don't want to do it with your hands, go to iFixit and look to, or Google anything. Like I thought you had as a key, like how do I, whatever, thing working, no? So you'll see a bunch of these black boxes. And that doesn't mean that they are all computers. How this happens, again, it's not about technology sometimes, it's more about the industry, it's more about convenience. When they found a bunch of things that they do, they work well together, let's say. An application that's common. So a small thing that you can put code inside and can do some operations and control some things. Okay, the microcontroller. Something that you can send some voltage to it and it can control motors which are really big. Something that can read the amount of time that you press a button and give a pulse according to that. When you find a use case for something, you build a circuit and say, okay, we are using this in 1,000 million products. Let's just make a small piece of silicon using that process that changed this big PCB we had full of components into something integrated. No? And that's why these things are called integrated circuits. So that basically means that not only integrated circuits, not all the black boxes that you will find around, you can program them. Many of the black boxes you will find around, you cannot program them. They are just things that you send some voltage in one thing, they do something else on the other, right? Even some are analog and not digital. One can even amplifiers, for example. We receive a voltage which is like this, and amplifiers and multiplies like that. And instead of having a bunch of electronics, you put them inside in a small black package. But it's true, many of these black boxes, they are microcontrollers. And microcontrollers work directly for any sort of programmable computer that you can put code inside and they do something. Okay, but just to clarify, sometimes like you open a piece of electronics, oh, I can put code in all that black box is. No, it's not like that. Might be that one you can put, and even let's say, if you go to the practical side, even if you can put code, it would be difficult if it's already on the electronics because you might not know how to interact with that chip. But let's move forward, okay? So let's understand a bit better what microcontrollers and computers difference is. Okay, so when we compute, in general, I mean, there's many ways. It's a long topic. People have studied 10 years and do 2 PhDs on that topic, so we cannot go straight into the topic, but we can just, let's say, sort around. So if we think on the idea of processing information in general, okay? So if we think on the idea of processing information according to some instructions that someone gave us, okay? That's how it will work, right? We'll just create some instructions, we'll write our code, like our Arduino sketch, and we'll put it into something, and that thing will get some information from around, or not even getting information, it's inside the program information, like multiply 2 by 2 and give you the result. And it would just throw us some results of that. To do that operation, it would be basically the program, something that looks at the program and tells what to do, and then basically a place where to store the data while it's doing that. So let's imagine, later we'll see, but if we want to do an operation of summing two values, so we need a code that tells us, okay, go and get value 1, okay, and now load it into the memory, go value 2, load it into the memory, and then we say, okay, now get value 1, add it to value 2, and store it in value 5. Okay, and I store it in value 5 and value 0 and value 3. Okay, and then I will need to go and say, okay, what's on value 3? Now, for example, put it out. Put it out. So we need what 3 somehow, which is a processor. We need a memory, which is like our desk, or desktop on the computer, where we place stuff, and then we need the instructions, which is like a receipt. So basically, at the beginning, the computers usually they had all the parts separated. So the beginning was like, okay, one unit is the one that's memory, one unit is the one that processes, one unit is the one that stores things for a long time, like the hard drive. One thing is the one that is designed to receive information, like a typewriter. One thing outputs things, like a printer. That's how traditionally all computers started for companies. And then basically what we did is we just miniaturized that. And now we are at the point where miniaturization is everything, but I think we all will remember that times and still we have. That's a PC, and if you ever open your PC at home, you have basically a processor, you have the memory chip, so basically information might come from your keyboard to these connectors here, and basically it would then go, the control side of the processor will store it from the memory, and then the processor will do something with your characters, like, okay, put them on the screen, good. Then you'll say save, then we'll go back here and say, okay, store them to the hard drive, no? So that's traditional computers, no? If you never did that, open one, it's fun. And you can put them together as you want. So let's go a little more on detail of how the architecture of the microcontrollers we'll be using, of these small computers that you'll use in Fab Academy works. So, first of all, let's clarify a little bit. So, computers, as we learned, can be many different things, okay? Traditional computers, as the ones they have an architecture where usually all the parts are separate. So we have usually, we have what's called the processor, right? Which is the core of what it really thinks. But this processor alone can do nothing. So usually you have the hard drive, right? Where you store your programs and your operating system, and you will load that into your processor. In fact, the processor will load that into the RAM memory, which would basically keep some of this information. And then it would go and check some inputs and outputs as a keyboard, and it would then get the information what to put on the screen and then send it to the GPU, which is another processor that takes care of the screen. And so it's quite a complex system, right? Designed on different parts. What has been happening so this whole computers started, right? And so I would say that at the beginning of the 90s, well, it started before, but the big boom I would say was the beginning of the 90s. We started to see what's called microcontrollers. And I would say now we are moving from microcontrollers to what's called more system on a chip. Basically means all these different physical parts, all these different parts here, the hard drive, the CPU, the GPU, blah, 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 blah. I can put them all together on a single piece of silicon. As we said before, I can make them all. Instead of having them on different parts, I can design them and put them all on a single black piece of silicon, and I can customize it to do whatever I want. And so there's a kind of these all-in-one computers, that are low cost and mostly designed to interface with the real world, to read switches, to send signals to motors, and these ones are called microcontrollers. And basically, how we'll use them and why they're cool is that instead of having to put on a board, so let's imagine a board, let's imagine how complicated it would be on a board like this having to put the processor, the memory for storing the program, the memory that you need to operate, so the RAM, the clock, well, the clock is already outside. But imagine having to put all the things on different chips. Just to do something like this, you would spend a week soldering, So they put everything on a single package, okay, and make it convenient to use. So mostly all the microcontrollers that we use in Fab Academy, and the ones that I use on the Arduinos, and the ones that you mostly use for your final projects, they basically have an architecture which is all similar. And in fact, and that's important to remember, all the computers that we see around, as we said before, that things got standardized a lot. All of the computers that still use the same architectures that were invented in the 50s on the idea of the core concepts. Innovation happened a lot. But all these architectures, mostly, it's a guy called the von Neumann architecture, which a guy called von Neumann, he's one of the fathers of computers. And then the one that these computers use more or less, the microcontrollers, is based on that. If you want to be technical, it's more called like a mix of what's called a hardware architecture, but it's the same. So basically, what happens inside a microcontroller? What happens inside these black boxes that will be soldering together? So we have a section dedicated to I/O. We need to read pins. We need to say, okay, it's the button press, it's USB connected, send me data from the USB, turn on the LED, read the button, control the motor, read the temperature sensor, put this on the screen. So we need an I/O section, okay? And that's inside the chip. Then we need the control. The control is a critical one because if we think how all this will start when we put power into it, we connect it. So this would go and say, look, the control will start first. And the control will go to the program memory and will load the first burst of code. And the code might tell me, look, go and check pin number 2 if it's on. So it tells me to check pin number 2. I go pin number 2, okay. And maybe it tells count how many times it's on. So it will be counting how many times it's on. It's on 2 times. Now maybe we want to multiply this by 2. So we will go and get this and go to the arithmetic unit, which is like a calculator, and would do the add multiplication of the operations it needs to do. And then we'll say, but while it does this, these two, they cannot host any values. They need a desk where to put the values, so they will store on the data memory the values. So we will be something like, hello, good morning, for memory, check pin number 2. I go here, pin number 2, the each press, okay, it's about to each press. Okay, each press is stored on data memory, okay. Then again, what I do is that, okay, check it again, check it too, okay, start here. And it's like, okay, now get these two values, for example, I multiply them. So I go here, get the value, I go to stream thing, I multiply it. And then, okay, now throw it by the blinks of an LED, for example, or by a value on the screen. So talk to the I/O. So at the end, there's this control unit that does everything. That's what's at the end. It's quite stupid what it does, but it needs to be really good at doing it. And then you have the arithmetic unit, which is also quite stupid. It can just multiply, divide, some, and then you have the program and data memory, which they don't think at all. It just store things, okay? And then you have the I/Os, which, well, from the point of view of us, it can be more complex, no? Because they can be I/Os that just are USB, or I/Os which are a simple on or off pin, or they can be controlling a full screen, no? But at the end, the core concepts are the same, and this hasn't changed. And when we code the program, we'll put it there, okay? Then we will put our code that we'll do to control the things we want to control. And that's how an Arduino works, right? And that's somehow that's what we can think as reference design for microcontroller boards. And the things you do in building at the end, they all will fit conceptually into what one Arduino is, for example. Okay. Um, so just quickly, an Arduino, I would say, an Arduino at the end is like we're going to call it. Let's say it's like a workbench. So basically, what's important is the processor. So that's basically like a workbench where we put our processor, that's the things, no? And then we just have a bunch of convenient pins and outputs and inputs where we'll connect things. And we have things as a USB connector, and because the chip cannot talk USB, we have a serial to USB converter, and we need the clock, and we put it there. So it's like a workbench where to play, you know? And it's also what we can call a blueprint, because it's a design that we can inspire, we can use to then build our things on top. But the power of it, let's say, what actually has all these different units, the memory, the program memory, the IOs, everything, is just this black box here with all these pins, okay? And that's the beauty. It's a difference to your computer where you have the hard drive, the RAM memory, the CPU, maybe the GPU, the keyboard controller, the whatever, trackpad controller. You have everything on a single package, and of course, usually cheaper. No? So a microcontroller like the ones we'll be using in Pap Academy, it costs from 50 cents to $4, €4, the more expensive. Okay, so that's the range. And compare that to the cost of a CPU like the one in your computer, which might be the cost of, let's say, from maybe 60 to 100 something euros, no? Depending on how, and just a CPU. And you have to put all the things around, no? That make it more expensive. So at the end, but the important is to think that what this does at the end, it's based on this, and you can replicate an Arduino like this. So you just need the processor and a way to provide power to the processor. That's a voltage regulator. Just puts 5 volts to the processor. You will need a clock to count the time because the processor doesn't require a clock, and you need an LED if you want to see that's working. That's not compulsory. So that's the idea. No? So we have a microcontroller, and we build things around that microcontroller to make it do whatever we want to do. We could connect here a motor, we could connect here a display, etc., etc. And that's how we build what we want around a microcontroller. And there's different microcontrollers. And in Pap Academy, we learn like, okay, that's better for that, that's better for the other. But better or worse is not like that's good for video, that's good for sound. It's like that can control 2 things, that can control 10 things, or mostly. Like this has more power, more memory, and it's faster. And I would say at the end, most of the time, it's the number of pins that you have, so how many things I can control, and how memory you have, so how big your program can be. You know? So the more program that you can put inside, the better, because you don't have to be optimizing, and you don't have to be placing things properly. You can just code and make it run. Okay, so at the end, these things are mostly about inputs and outputs. No? So we can think about, okay, we'll read inputs, we'll do some processing, and we'll output something. And I think that's the idea we just need to be clear now, is that we'll do some code, we'll put it inside the machine, that's a computer, that's called microcontroller, and it will be able to read inputs, do some processing with that data, and turn some outputs. And that's the only thing we need to keep in our minds. As I was saying, and to get a little bit of perspective, so that's the computer that went to the moon, the one that I showed you, the one that fostered the industry of integrated circuits. And that computer, and that's an Arduino. the Mega 328, which is a microcontroller you will use at Top Academy. That's the Raspberry Pi that you might know. I think it's version 2, I put here 1, I don't remember. And that's an iPhone 6, okay? And you can see the skeleton of it. So we can say that an Arduino is more or less similar to the computer that went to the moon. In some terms, it's faster. In fact, it was running at 2 megahertz, and the Arduino runs at 16 megahertz, while the Raspberry Pi runs at 700 megahertz and has two processors, so dual this. And your iPhone 6 is 1,400 megahertz and with two processors. So the speed of processors has moved really, really fast, and that's why your computer can easily now show you and do things that make you feel that you can run things in parallel, which never happens. Your computer is not able to play a movie frame while it's playing an MP3 song, while it's showing you notifications, while it's downloading a movie. It can do all that because that's one after the other. But because it's so fast, you feel that things are happening at the same time. Well, of course, some processors now they have 2 or 4 cores, but then we never have as many cores as applications you are running. This feeling that things run in parallel, it's just because things are really fast. So of course, with the Apollo computer, you don't have that much feeling that things are running in parallel. You had it already because they were really smart in the way they coded, but yeah. And the memory. So the memory, this will be like the size of your desktop. It's like how many things can run in parallel. So you look here, that's 4 Ks of RAM. The Arduino is a little less, so it has less memory than the Apollo computer, but still it's like pretty similar. If you think on a Raspberry or an iPhone, it's orders of magnitude bigger. So at the end, the conclusion is that the Arduino is really, really low power. But even though you can do many things, because at the end, what requires a lot of power is processing video and processing audio. So if you don't need to process video and you need to process audio, you can do it with Arduino. And you can even do with Arduino audio and video. And there's similar chips nowadays that allow you to do that, like the Raspberry Pi, for example. And that's the amount of software that you can store inside. You know? Software can be programs that do things, or even information that for a long time, like images that you want to store for longer now. So you can see like, it's interesting here, you see it says flash, 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 and here it says ROM. That's because the program memory of your computer was fixed. So you put it there, and you cannot change the program. So it's there inside, and every time you start it, it would do that, okay? Rather in the Arduino, it's a flash, so you can change the code. You can load one code. Oh, that's for bleeding LED. I put another one that's for measuring temperature, etc., etc. No. But so you have this data there. It's fancy to see how things change. And in some ways, sometimes, no, I don't like a lot this table. I'm not a big fan, but sometimes it clarifies a little bit. You'll see when you search on web pages like Make Magazine, Hackaday, it's like, oh, we do this with a BeagleBone, we do this with an Arduino Zero, we do this with an Arduino NKR 1500, we do this with an Arduino Uno, this with a Raspberry Pi. And well, what's the difference between all that thing? So that's a table that compares them. At the end, I would say that once you know all, you know them all. It's not about the specifics, it's about the ideas, no? So, let's go a little bit more, okay? We said hardware, no? Now we understand. So, to go quickly, at the point we are now, we know electronics, bunch of components like transistors, resistors, and capacitors that we need to put together to make a computer. We put them together. We start using them a lot. We create an integrated circuit that contains them, okay? And we have CPU. Then we say, look, we want something cheaper, and we put inside a big piece of silicon the memory, the hard drive, and everything. And we have a microcontroller. And now it's time to put some code inside, so this computer actually does something that we want to do. No? So, importance. Something to clarify, because you'll see it quite a lot. Like, okay, so we have on microcontrollers, okay, which would be, let's say, for example, an Arduino that has a microcontroller. Usually what we call the software that we put inside is called the firmware. But you can also call it the sketch or code or as you like to call it. On, let's say, more powerful computers like the Raspberry Pi, which are more similar to your laptop or your phone, usually we have something called an OS. So that means that we have an extra layer of complexity on top of our code. And I think I have an image here, yeah. So basically, on the code that we have Academy, you have your hardware, and in top you put some code, okay? And this code will do things. Will read this LED, on this button, on this LED, blah, 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 blah. And then just your code and the hardware. Okay, there's a piece of code inside your computer, inside your Arduino, inside your microcontroller. It would start, it would run this piece of code, and if it's on a loop, it will keep running, it will stop, nothing else, okay? On more powerful computers, like a Raspberry Pi, like your laptop, like your phone, we usually have what's called an operating system. And that means that we have a code that basically is designed to manage other codes. So basically, you have an applications like Microsoft Word, like Blender, like GIMP, like even the Finder, that shows you the things on the screen of the folders, applications that will be managed together by an operating system that would take care that one application can run on the other two and would make you feel that all the applications that run at the same time, for example, or would provide functionalities as, okay, a program needs internet connection. So the OS says, oh, you want internet connection, give me internet connection, okay? Rather here, you have to manage everything yourself. It's like you are alone, okay? So basically, you can create your own operating system on top of here. So it's like the code and the hardware, nothing else, okay? That makes it really fast to understand, but also more complex to do difficult things, as for example, making tasks in parallel. And you'll see when you start coding for Arduinos, one of the things that strikes in your mind is how do I make things in parallel? Because this thing can just do a single thing at a time. So I need to think how I make things in parallel on something that's completely serial. Okay, so we are moving to the end a little bit. So we are talking about languages, no? We understand that we need to put some code inside the microcontroller that we'll call we will like the application that we run, okay? Like we'll do an application for a microcontroller, and this application would be, we call it the firmware, but you can call it the sketch or the code as you like. Compiling, okay? So basically, many people always like compiling. Okay, what's that? Okay, let's see how these humans have designed ways of controlling machines. And to do that, we create that idea of computer languages. So human language is one of the most powerful tools that as humans we develop, if not the most powerful tool that we have, because it allows us to not just communicate, but to abstract the world we live in into a specific set of symbols that we can share. So we needed a way to do the same for computers. And we need a way to computers from one to the other. We need a way to interface with them, to tell them what we want them to do. We need a way to write receipts, putting receipts at the end. So we created programming languages. In Fab Academy, you will see different languages. I would say for microcontrollers, you will see C and C++, which is like the evolution of C. And you will see Arduino, which is like a version of C++. It's even C++ straight on, but just presented on a nicer way. These are quite old programming languages. When they were born in the 70s, they were like the newest thing ever. Like C was like, that's super good, that's super fast, or more than fast, that's super easy in the sense that it's fast wasn't. That's something that allows to abstract the ideas we want to put on the code easier. Now when you think on C, it's like, oh, it's that thing which is a bit old, and it's like, it's for hardcore people. But for microcontrollers, we must use C because you can compile it and make it run on microcontroller easy because you are quite close to the hardware, even you are not on the hardware at all. And so it means that you can make a microcontroller which is really poor in resources, as we saw on the examples that I showed you. If you compare it to an iPhone, how small it is, but by coding it in a language like C, you can still make a lot of things. If you will code a microcontroller in a language which is more complex, language which it's, let's say, easier to code, that has many functions inside built in, it will be able to do less things maybe, a little bit Arduino helps to bridge that gap without even changing the language, because it's still C++. And so, at the end, basically, how this works, and that's that example, I mean, that's not a computer science example, it's just a basic example for us to understand the concepts, but how computers work is that, so we said we have this control unit before, you remember, and we have the arithmetic logic unit, or the arithmetic unit, okay, so we have the control unit, and the control unit is the one that looks at the program memory, where the instructions are stored, and where your code is stored. And so your code stored there needs to be stored in a way that your computer or your microcontroller can understand. And this is done by using a set of instructions that the computer can understand. So all the computers, all the microcontrollers, they have a list of instructions that they can do. And the idea is that with these instructions, you can do everything. And to think about that, think while you're cooking, right? If you write a receipt for cooking, you can write, okay, put the chicken on the oven, okay, and then your computer will need to understand what an oven is and need to understand what a chicken is, or you can describe it as, okay, move your right hand 40 degrees, get what's or in front, right? And you can simplify these instructions, which can be just move the amount of degrees that you want, right? Maybe, and the direction that your body is pointing. So you have few instructions, right? Maybe let's say a simple instruction which is move, and one which is cut, maybe, one which is feel, no, or not even, because to feel we just need to move things, no. So we can simplify things into a few commands, right? And still make it. You'll have to write more, no? But machines usually prefer that. They prefer things which are complex, a lot of simple but easy to do tasks, rather than things which are, as we like mostly, no? Which are one single thing but difficult to understand. And that's the kind of thing we like the most. No? We get bored as humans when we have to do things which are simple to do one after the other. But computers usually are the opposite. So the one we do is this. So for us, this makes a lot of sense, right? It's like, okay, we want to sum two numbers, right? For the computer inside, what it will do is, okay, it has few instructions as this move and feel and instructions that we say when you cook. So one is like, okay, load into the register, load into the memory number 1, okay, this here, okay, and load it into the memory on, let's say, the drawer number 0. Now get number 2, okay, and load it in the drawer number 1, okay. So that's the instruction which is it's used for loading things. Like get this and load it into a drawer. You say, okay, that's the drawer and that's the value what you put on the drawer. Then you go to the next one, and it's the one which is it's like a calculator. It's like adding. It says, okay, add what I put here, okay, what is in drawer 0 with what's in drawer 1, and I store it in drawer 5. And then I say, okay, now store what's in the drawer 5 into something which is called sum. Okay, so basically, something like this is not that the computer understands, let's say, the complexity of this, not the computer has an instruction to represent all sort of operation. It basically maps everything to simple instructions as load this there, sum it with this one, compare these two things. So let's say if this sum will be of 10 values, the only thing that this would do is to start adding these. So we would first add these two values, and then it would get R5, and using the other, it will submit with another value that might be stored in R7. And it will just, this be longer and longer and longer, right? So really basic tasks like adding, no, you can't just add two values together, no? This and that. So if you want to do 10 or you want to sum 10 or 15 values, you will just keep doing this instruction after and after and after. And every time you will add, no, the result with an extra value. No? So I don't want you to understand this at all as the complexity it represents, but it's just the idea of, okay, using really simple instructions, so using an instruction that just can add two values, in fact I can add as many values as I want, as far as I do with one and again and again and again and again. No? And that's the importance of these ideas. So when we write code in C++, for example, for the Arduinos and for the microcontrollers, we'll be just compiling code that will look like this, okay, into something that will look like this. And then from something that looks like this, we'll turn it into what's called machine code. That would be something like this, but represented in binary, so in zeros and ones. That would be what actually our memory would store. And when we put power into the microcontroller, it would start running one after the other. So, right, as I said, we'll put some code and we'll put it inside one of those small pieces. And that's at the end what happened. We don't need to understand it now, we'll look in another class, but there's something called a compile chain, which you'll do these days. You'll learn something called make. And make basically, it's just a wrapper. It just, let's say, it's a piece of code, it's an application that helps to automate tasks. So you'll see these days, you'll run make on your computer and you'll get the code, and you get the code, and with the code you compile it, and then once you have it compiled, you basically will use something called AVRView to put it inside your microcontroller. No? So you have basically a process where you look at your code, you compile it, so you turn it into a machine code, you turn it into something that the computer can understand, right? And then from there you'll put it inside, no? So, and everything it's automated with a tool called make, so it's having to remember all the different applications you make, and it does all the steps at once. The last bit for today, okay, that's the last thing, It's what's called flashing. So that's why you are doing that assignment, and that's interesting. So two concepts, programmers and bootloaders. Why you are building an ISP? Why you are building this board that has a USB on one side and something on the other side called in-circuit serial programmer. So you are building. Okay, you have one here. So what you're going to build next week, or this week in fact already, tomorrow, no? It's something that it's like this. So that's a commercial version of it, okay? And you'll build it yourself. So you don't have to pay 60 or 100 euros. I don't know how much they charge you for that.
The new one, I don't know.
The new one is too expensive. So what is that? Look, the chip, okay. You'll be designing on the future on next assignments. You'll be designing boards. Boards that will be like Arduinos, right? We'll have a microcontroller, right? And we'll have LEDs and buttons and sensors, and you'll be able to read from them, etc. You'll need to put inside of them the code, and you will say, "Oh, why I cannot plug it over USB to my computer now and put the code inside?" Well, the problem is that these microcontrollers natively they don't talk USB. You need to put code inside so they can talk USB or they can talk. So you need to make a specific piece of hardware that's able to talk to your computer, get your code, and put it inside the microcontroller. And that's what's called a programmer. So in fact, well, yeah, that's it. And let's move forward. So basically, if we look at a traditional Arduino, well, as the Arduino Uno, maybe some of you already played with it. It's this blue board, right? So you will see on an Arduino basically what you have is that you have what's called the Amiga 328, which is this thing here. That's the black box that we saw. That's this thing, okay. And the problem here is that that thing, it doesn't talk USB. So you cannot put code inside of your computer because computers nowadays, they just have USB ports and HDMI ports. They don't have like serial ports anymore and things like that. So in fact, that thing can just talk serial. And if you get an old computer, I don't know if we have any old, no, we don't have any old computers here, but if you get any old computer, like the ones controlling some of the lasers or the milling machines there, you look at the back, you'll see these ports that usually they are that size, and I think the standard for color now is yellow maybe, I don't remember now. Well, that's where serial ports. So computers, microcontrollers before, they all used to talk something called serial. If you had a printer on the 90s, it mostly talked to serial. If you had a modem to talk to the internet, it had serial. So these things, they talk serial. So if you want to put code inside, let's say, you mostly would talk to them through serial. But what happens is that your computer, it just has basically USB. So they had to put something here to translate from serial, right, to USB. And you'll see something called FTDI, which is a cable that basically does this conversion. So you can talk to your microcontroller using USB. But this talks serial, and it can't talk USB, right, through an adapter. But at the beginning, when you buy the chip, it cannot even talk serial. It's dummy. It's empty. So you need to put code inside so it understands that it can talk serial and USB, and you can start programming it from here. How do you put that code inside? You put it through that connector here. So when you buy an Arduino, that code is already inside. Is this thing here, okay? Through that port. What you're going to build is a tool like this, but DIY, so you can design any circuit that you want, put chips from that company called Atmel, and then be able to flash them, so be able to put the code inside, and even not just put the code, put code inside that later on might be able to make your chip directly programmable through USB. Okay. And so the idea of making this is just because it's like a thing, something you have on the toolbox. The one you're going to build, a FAP ISP, allows you to program chips from a family called AVR, which is a big family from Atmel, and most of the Arduinos use that family of microcontrollers. Okay. So let's move ahead and finish that. So basically, and just to look there, to let's say check it again. So that's the big chip in black that you saw there, okay? And that's the small chip that you had there. And the sizes don't even correspond that creation figure. So that's a small chip. That chip, so we start from here, okay? And so we have this connector here, which is the one you saw at the end of the board. That is where you will connect your board, right? And your board basically would be able to feed through that port code inside this computer here, and then this computer would be able to talk serial, and then through serial it would talk serial to that thing here, and that thing would talk USB. So you'll be able to put from USB a straight code to your microcontroller. Anyway, this is for the Arduino wall. You will move forward at the end. The concept for you need to know is forget about all that thing and just think that the chip you'll be working on, you'll need a programmer always to program them, and that you'll build your own programmer. That's the only thing. And you'll build your own programmer using the same tools. So it's kind of a chicken and egg problem. So you will always need one of them to flash your programmer. So on your programmer, it will look like this at the beginning. So you'll need to put code inside through here. And so the first one will need to use that, and then all the rest will be able to use your colleague's programmer. So, and it's quite cool. You start with one like this, and then you can program one. When you have one program, you can program the other, the other, the other, the other, the other. And it's very because it's really cheap. That in parts of API would cost maybe less than 10 euros part, and this costs maybe 70. And it doesn't make any sense. It's nice to be able to do it, and you learn too. So, having said that, I think we'll go more into Arduino, okay, later on. But hopefully this gave you a wall introduction to this wall, okay. Just before we finish, and I don't want to annoy you more, but just to finish. Um, okay, just to finish clarifying a few things about what we're going to build. So that's a FAB ISP, okay, and it has here these connectors, right? The same as the ones we look at the Arduino, right? So, and it has here a USB connector, and we'll use a chip called an Tiny44, which is like a microcontroller that you can program, right? So you won't need to program it because what you want him to do, which is from USB create this protocol, no? Like from USB go to a protocol which is called in-circuit serial programmer to program your chip. That's it's a code that's for all of you the same. So you don't want to customize it. So someone at App Academy already created, and so you would just need to download the code and put it inside, right? And the power of this is that this microcontroller, as you say, it's a general purpose computer as we discovered before. So we'll code it here to do that process, but you'll encounter on the week after, you'll use it to read temperature and bring it to your screen, and the week after you'll use it to control motors, etc., etc. You know? So basically you are using, instead of having a dedicated chip that we buy from the manufacturer that is able to do USB to in serial circuit programmer, we'll just put an off-the-shelf chip and put the code inside and make this behave as USB on one side and as this in serial circuit on the other.
This chip is a JTP?
It's an, yeah, exactly. It's an 80 tiny 44. So it's like the 45. Sorry, I am saying right. Yeah, 44. You're right. It's like the 45, but with more bits. So it's 4 Ks of flash memory. In terms of RAM, I don't remember.
It's from Atmel.
Exactly. It's tiny
in the family of ABR.
Exactly. Super. So it's Atmel. Atmel does now ARM and ABR. Beside ABR, you have Atmegas, which are the Arduino family, Atmega 328, 168, etc. And then you have the AXMENO family, I think, which is really not that well known, and then the Atmega. And so on Top Academy, mostly we work with two families of processor, Tiny and Atmega, like Mega and Tiny, is easy to remember. And these are the Tiny, which are really small, and that's Tiny 44. Just what time it is? Do you have time? Okay, so I guess you are really tired. You want to do a short break and move into that? Santi, how is this timing for you? You want to do this quickly?
So we have a busy.
Perfect. So let's just solve some of this quickly, and we go. And if you have more questions, it's time free. Let's just. So.
So family is ABR programmer.
Exactly. FabXP is an AVR programmer. Well,
The manual itself, you have just.
yeah, let's try to. I just move it there because
it's like when I give redundant questions when you might not.
Okay, so I did that, because sometimes the problem is that I did that because if we ask for questions now, all the questions will be on the ADR, and I think the important is to solve sometimes more general questions, So, how do you stop feeling intimidated by electronics? Someone say, well, we all feel intimidated, but I think the point here is that it's like that things in life, where you really have to think that it's not about feeling you're not intimidated. I think it's about, you go and you say, okay, I want to solve that, and to solve them I need that, and then you go for that. It's a bit kamikaze style. I think it's the best. So it's like, no, it's like, I want to solve that. I want to make something that's really cool because I wanted to make and doesn't exist. I want to make that thing that blinks. I would want to buy, and I will make it, and you go straight for it. I think that's somehow the best. At the end, I think it's mostly about not being scared of copying and copying and copying and looking what's on the internet, copying exactly from their learning. At the end, I brought a lot of theory today, but just so you know it a little bit. But from now on, you forget and you go with that. What's the point of electronics? I think the point of electronics at the end is that if you want to make anything that somehow thinks, is a convenient way of doing it. It's not the only one. We can make complex mechanical things. We can make materials that react. We can even make materials that think somehow. I don't know will like that thing, but it's one of the ways to make things that react in a convenient way nowadays electronics, because it's the way we build stuff. It's something that we decide how everything works. So how much we understand, I don't know, that depends, but it's not legal. What microprocessors are going to use? Okay, what we say, what microprocessors you're going to use. So you'll use mostly Atmel. So you'll use all the microcontrollers, from a company called Atmel that was acquired by Microchip. So now it's Microchip in fact the owner. These microcontrollers from a company called Atmel and a family called ADR. They were super new and modern by the late 90s. They were a big revolution. And there's two families, the Tiny and the Mega, and that's the same microcontrollers that the Arduino family of products use. So what you are learning here, it's completely, let's say, it would work straight off with the Arduino wall. So even though Neil might not be using the word Arduino that often, what you are learning would make you a master on the Arduino wall. Okay. And what kind of programming languages? Well, in Fab Academy, mostly it's like will be C++ or C, which we can think as the same at the moment, with Arduino on top, so we might be easy to use sometimes, or without Arduino. You will see Neil provides examples with no Arduino on top, so it's Bareboard C, C or C++, while in some other examples we use Arduino that simplifies life a little bit, and we'll do a session on that. Then on the interface programming class, then you will go in more crazy. You'll be able to use Python, JavaScript, PHP, Ruby, whatever language you want. I think mostly we'll do Python processing and JavaScript maybe. No? Can you answer? Sorry, yeah, knowledge only. I would say, yeah, someone talks about recommending books. We start the links. Sorry, what is okay? Someone asked, what is ADR programming? What is 8 Hz at speed? Okay, yeah, right. So, programming we have it clear now, no? The microcontrollers we'll use are computers. As we install Windows in your laptop, we'll need to put code inside. And we'll put it with a device that's the same as this, but that you will make your own. Then, me yesterday talked about the clock, no? 8 megahertz clock, no? What's that? So, any computer like your laptop or needs a precise timing, because time is much more important than we think. Our brain has time integrated in the back, and so we just think on time when we are late, and when we need to count how fast we go in a race. But time is what allows our brain to understand that time changes, and that's critical. Imagine that we lose a sense of time. We won't be able to perceive reality. We will just perceive still frames or something crazy, I don't know. So computers are the same. They need precise account of time, not just for telling you the time. They need a precise account of time because just to communicate with another computer, for example, while the USB talks to your computer, they both need to agree on time, So time is really important on this. And so on this, when we put the microcontroller, we always put a timer nearby, a crystal, something that counts time. So an 8 megahertz timer is basically a piece of quartz, and when you put electricity on it, it doesn't spike every 8 megahertz precisely, and so basically it keeps time precise. It's like the counter, it's like the second on the clock, let's say. Okay. Then more. What is the key? Minimum knowledge required to make electronics. Well, we say this thing changed a lot. No, before was like to make electronics, you need to study a whole career, and of course to make many things you need to. But I think you can make a lot by learning documentation which is online. Important to know what we are on Fab Academy, more than electronics, I have the feeling you learn electronics, you learn also programming too. No? If you have questions about electronics, like how I control this, there's books about Arduino, there's some other information that we can share you. Is there anyone who can build a very simple computer? Admil, okay. Really? Admil, that's sort of more technical. Maybe we can discuss it later. But mostly the point here is like, okay, someone is asking why we use just, I don't want to go technical, but why we are going to use these tiny computers and these Atmel computers, no? Why we're going to stick with this manufacturer called Atmel and not use other things. We'll use them because they are really well known. The compile chain, so the tools that you need to put your C code. So the tools that you need to get this C code that we set here. So the tools that you need to turn somehow this into that, they are fully open source. Okay? That doesn't happen for other families. There are families that you buy the chip and you're a company like Volkswagen and you want to do the new airbag system for your cars, and you need to go and pay the company who makes the chip license as, let's say, a SolidWorks of 10,000 euros. So they give you the software that might allow you to compile this into that. That's not reason. It's fully open source, it's been open source for many years. And then another one